Welcome to the deep dive. So imagine this grand quest, right? A dream to build this perfect, all-knowing system where every single mathematical truth could actually be proven.
Yeah, the ultimate certainty.
Exactly. But today, we're diving into a story that really challenges that dream. It reveals these fundamental limits to what any formal system can truly know about itself. And our guide is Kurt Gödel. His work gave one of the most, well, astonishing counterintuitive answers in modern thought.
That's absolutely right. For centuries, the ideal in mathematics was this complete system, where every true statement could be formally demonstrated, laid out step by step.
Right.
And Gödel just showed that this ideal, well, for any system complex enough to handle basic arithmetic, it's fundamentally impossible, unattainable.
So our mission today is really to unpack Gödel's incompleteness theorem. We want to explore how he showed why some truths in math are just inherently unprovable and, how he even got to this conclusion that just rocked the entire mathematical world.
Mm.
It feels a bit like watching a master illusionist, doesn't it? Because Gödel somehow managed to sneak the very essence of a paradox right into the heart of mathematical logic itself.
It's really fascinating. And the initial start, apparently, came from these seemingly simple paradoxical statements, like the classic, "the sentence is false."
Right, the liar paradox.
Exactly. But the genius move was figuring out how to translate that self-referential structure directly into the language of mathematics.
Mm.
And in a way, nobody thought was possible.
Okay, let's set the scene a bit. To really appreciate Gödel's breakthrough, we kind of need to understand the mathematical world he walked into.
Yeah, the context is key.
So, by the turn of the 20th century, math had become this incredibly precise, symbolic language. Thanks to centuries of formalization, people like Descartes using letters for variables, Robert Ricord inventing the equals sign.
Yeah, it had come a long way from just being written out in sentences.
Right. This precision was vital because before that, math was often quite descriptive. But as it evolved, especially 17th to 19th centuries, it got super formal. Yet there wasn't always a clear, agreed-upon standard for what was truly rigorous.
Exactly. And paradoxes started popping up, like some Euler discovered. And these raised serious worries about, well, how reliable is mathematical reasoning really?
So the big ambition was total mathematical certainty. Like, create a system so perfectly airtight it could never be challenged.
Precisely. That period was driven by this incredibly powerful desire to nail down mathematical truth once and for all, build an unshakable foundation. Lots of brilliant people worked on it, but the most monumental attempt came from Alfred North Whitehead and Bertrand Russell.
Ah, yes, Principia Mathematica, their huge 3-volume work, 1910 to 1913. And this wasn't just a book, was it? It was this incredibly noble attempt to formalize all of mathematics.
The whole thing. Unite it with logic, set theory, ground mathematical reasoning definitively.
It was really seen as the ultimate dream realized, wasn't it? A precise, formalized system for everything. They really thought they'd built this fortress against paradox.
Their absolute core goal was to eliminate paradoxes completely. Russell especially was convinced these problems came from self-reference. Statements talking about themselves, sets containing themselves, that kind of thing.
The messy stuff.
Yeah. So, to fight this, he developed something called the theory of types.
And this theory of types, that was his big defense mechanism, right? Like an incredibly elaborate hierarchy.
That's a good way to put it.
Yeah.
A hierarchy to prevent self-reference. Sort of like saying, okay, a statement about numbers is on one level, statements about numbers is on a higher level, and they can't mix in a way that creates loops.
Like a folder can hold files, but a file can't hold the folder it's actually in.
Exactly, that kind of idea. Keep everything neatly layered to stop any statement from referring back to itself. And honestly, was it seen as the ultimate solution back then? Absolutely. For many, many years, Principia Mathematica was hailed as the achievement. They genuinely believed they'd built this unbreakable wall.
But Gödel found a way through.
He showed that even a seemingly perfect wall has these, well, invisible cracks. Not because the wall itself is faulty, but because of something inherent in the structure itself.
Okay, this brings us right to understanding these formal systems. When you say rules without meaning, my brain immediately kind of glitches on that. How can math, which feels like it's all about truth and meaning, just ignore what its symbols represent?
Well, think of it like a game, maybe chess.
Yeah.
You've got pieces, those are your symbols. You've got starting positions, those are your axioms.
Right.
And then you have very strict rules for moving the pieces. Those are your rules of inference. But crucially, the pieces themselves, the knight or the pawn, They don't mean anything within the game beyond their defined moves.
They're just shapes you move according to rule.
Exactly. It's a system that operates purely on the form of the symbols, not on what they might represent in the outside world, like numbers or whatever.
So these axioms, these starting points, are the absolute bedrock rules. Like, there's no number whose successor is zero, basically. No negative numbers in this basic system.
Right. Or 0 is an additive identity, meaning adding 0 doesn't change your number. Properties of addition, multiplication. These are the formal notations you start with.
And the rules of inference are how you manipulate them.
Precisely. You just look at the symbols. If a sequence has a certain form, you can transform it into another sequence according to the rules. It's purely mechanical, like a machine following instructions based only on the shape of the inputs.
Okay, so we've got these system symbols rules, but what does it really mean to prove something within them? What does a proof look like?
Well, that's where it gets interesting. You might start with a really short statement, like 1 + 1 = 2.
Seems simple enough.
But the proof process, the sequence of steps transforming axioms into that final statement, can involve incredibly long, intermediate strings of symbols.
Really?
Oh, yeah. And they can zigzag in completely unexpected ways before eventually landing on your short result. The length of these intermediate steps, the number of steps needed, it's totally unpredictable. It's not a simple, straight path.
That unpredictability is key then. I remember reading that Bertrand Russell was so sure his system, Principia, was free from self-reference problems.
He was very confident.
Because when you write down statements about integers, even complicated ones like Fermat's last theorem or the Goldbach conjecture, they just seem to be about numbers. They don't look like this statement is false. How could self-reference possibly creep in?
That was exactly the thinking. They were talking about integers, primes, addition, multiplication, properties of numbers, not about the system itself. They really truly believed they had banished those paradoxes.
Okay, so let's nail down this key difference. Well-formed formulas versus theorems. A well-formed formula, a WFF, is just a grammatically correct statement in the system's language. It could be true or false.
Right, like 1 + 1 = 2, that's well-formed and true. 0, 1 is also well-formed, but it happens to be false.
And the crucial thing about WFFs is
How easy it is to check them. You can mechanically, predictably tell if a given string of symbols is a well-formed formula. It's like checking parentheses in code. You can break it down recursively. It's a trivial, predictable process.
simple check. Got it. But a theorem is different. A theorem is a well-formed formula that actually has a proof, a demonstration starting from the axiom.
Exactly, and this is where the difficulty explodes.
Yeah.
It is not easy, not mechanical, not predictable to know if something is a theorem.
Why not?
Because checking requires searching through the potentially infinite space of possible proofs. You have no idea how long that search might take or how incredibly long the intermediate formulas in a potential proof might be. There's no guaranteed method, no predictable timeline.
Okay, analogies might help here. Let's drive this home.
Good idea. So think about checking if a number is a Fibonacci number. That's like checking if a formula is well-formed.
Right. If I give you, say, 377.
You can just generate the sequence 1, 1, 2, 3, 5, 8, and very quickly and predictably see if 377 shows up.
Easy peasy.
It's predictable. Now, contrast that with something like the Collatz conjecture, the 3n + 1 problem.
Yes, the one where you divide by 2 if it's even or times 3 + 1 if it's odd. And supposedly everything goes to 1 eventually.
That's the one. The rules are dead simple, but the pathways numbers take, utterly chaotic and unpredictable.
Like the number 27 you mentioned. It goes way up before coming down.
Way up to 9,232. And even though it's been checked for billions and billions of numbers, nobody has ever been able to prove it works for all positive integers.
So that unpredictability, that's like trying to find a proof for a theorem.
It's a perfect mirror. You just don't know how long the proof might be, what twists and turns it might take, or even if one exists at all. It's that kind of deep unpredictability.
Okay, so we have these simple rule problems that are wildly hard to prove. Now, imagine Gödel taking that very unpredictability and weaving it into the fabric of math statements themselves. This is where it gets mind-bending.
Exactly. This is Gödel's revolutionary insight. People knew for ages that numbers could simulate the physical world, planetary orbits, physics, whatever.
Right, modeling things.
But Gödel realized something profoundly deeper. Formal systems themselves, their symbols, their axioms, their rules of inference, even the whole process of building a proof could also be simulated using integers. Manipulating symbols was just another mathematical operation.
Wait, so the system's rules could be represented by numbers?
Yes, he had this astonishing idea. What if every single symbol, every formula, every axiom, heck, every entire proof could be represented by its own unique integer, a Gödel number?
Like a barcode for everything in the system.
Kind of, but much more powerful. Think of encoding a piece of dock music into one single gigantic integer. Then asking questions about the music. Does it contain a certain motif? How long is it? Becomes asking mathematical questions about that huge number.
How did he even do that? Assign a unique number to potentially infinite formulas and proofs.
The brilliant trick was using unique prime factorization. Every integer breaks down into primes in only one way, right? So he assigned numbers to basic symbols, then encoded sequences of symbols using sequences of exponents on primes. 2 to the power of symbol 1's number times 3 to the power of symbol 2's number times 5 to the power of symbol 3's number, and so on.
Ah, so the sequence of exponents uniquely represents the sequence of symbols.
Exactly. A huge integer's prime exponents decode into a sequence of smaller integers, which then decode back into a specific string of symbols.
So a whole axiom, like for all A, it's not the case that the successor of a tire equals 0 could become one massive integer.
One single gigantic integer. And crucially, this integer is both a number within the system, you can do arithmetic with it,
Yeah.
and in the context of Gödel's encoding, it represents that formula.
Wow. Okay, what are the implications of that for testing things?
Well, remember how easy it was to check if a formula was well formed?
Yeah, mechanical, predictable, like Fibonacci numbers.
Same thing here. You can mechanistically tell if a given huge integer stands for a well-formed formula. There's a predictable algorithm to check the structure encoded in its prime factors. It's easy.
But I sense a but coming.
But, and this is the absolute core of it,
Yeah.
you cannot mechanistically tell if a given integer stands for a theorem number.
Ah, because proofs are unpredictable.
Exactly. Proofs, when encoded as these Gödel numbers, inherit that wild, unpredictable, Collatz-like nature. Determining if a given integer g happens to be the Gödel number of a proof of some statement is a profoundly complex, non-mechanical question. He embedded the Collatz problem's difficulty right into the heart of provability itself.
Okay, so this leads directly to his big result, the unprovable truth. Russell and Whitehead tried so hard to kick self-reference out.
They built fortifications? The theory of types?
But Gödel, using this numbering trick, basically snuck it back in. A Trojan horse made of numbers.
That's a perfect analogy. He constructed a very specific string of symbols. Let's say its Gödel number is g. And this string, when you decode it using his own system, essentially says,
What does it say?
the statement whose Gödel number is g is not provable within this system.
Which means?
Which means the statement is effectively saying, this statement is not provable.
Whoa, okay. Back to the liar paradox, but now inside formal mathematics.
Precisely. Now, think through the implications. What if statement g were provable?
Well, if it were provable, then what it says, I am not provable, would be false.
Right. And a formal system that can prove false statements, that's a disaster. It's inconsistent. It collapses.
So to keep the system consistent, which Principia Mathematica was assumed to be,
Statement g must not be provable.
okay, it's not provable,
Yeah.
but then, wait, if it's not provable,
Then what the statement says, this statement is not provable, is actually true.
oh my God, so he constructed a statement that is undeniably true, but cannot be proven within the system.
That's it. That's the incompleteness theorem. A true but unprovable statement right there in the heart of arithmetic.
That really is the mathematician's nightmare. The bedrock belief that truth and provability were essentially the same thing, just shattered.
Completely shattered. It was a profound shock to the foundations of mathematics and logic. For those who thought every true mathematical statement must, in principle, have a proof waiting to be found, this was a fundamental, unavoidable limit.
And this wasn't just a weird quirk of Principia Mathematica, right? This applied more broadly.
Much more broadly, Gödel's construction, his method, wasn't tied specifically to Whitehead and Russell's axioms. It applies to any formal system that is consistent and strong enough to express basic arithmetic.
Yeah.
Peano arithmetic, Zermelo-Fraenkel set theory. Any foundation rich enough to talk about whole numbers will have these unprovable truths.
So it means that in any sufficiently powerful mathematical system, there will always be true statements that the system itself cannot prove.
Always. And you can't just find that unprovable statement G and add it as a new axiom to fix the system.
Why not?
Because that just creates a new, slightly larger formal system. And Gödel's method can be applied again to this new system to find another true but unprovable statement within it.
So it's like infinite holes. You plug one, another appears.
Exactly. An infinite hierarchy of unprovable truths. You can never create a single formal system that captures all mathematical truth for even basic arithmetic. The system can never be both consistent and complete.
Okay, but initially, didn't these Gödel sentences, these unprovable truths, seem kind of artificial? Like maybe they were just clever logic tricks involving self-reference, not the sort of natural problems mathematicians actually worked on day to day.
That was definitely the feeling for a long time. They seemed a bit esoteric, cooked up specifically for the proof. Important, foundational, yes, but perhaps confined to that logical realm.
But that's changed.
Dramatically. In more recent decades, mathematicians like John Conway and others started finding connections. They showed that this kind of Gödelian undecidability actually applies to very natural, concrete mathematical problems.
What makes that so astounding?
It's not just that these problems are hard to solve. It's that they are provably unsolvable within our standard mathematical frameworks for reasons directly related to Gödel's theorem. It's like finding out some jigsaw puzzles literally cannot be completed, not because you're missing pieces, but because the picture itself contains a contradiction that prevents it from fitting together within the rules.
So like those collapse-like sequences you mentioned, the 3n plus 1 thing has cousins, like 5n plus 1 or whatever.
Exactly. It turns out there are specific problems in that family of simple iteration rules that are undecidable for precisely Gödelian reasons. Their truth or falsehood is equivalent to the consistency of the underlying mathematical system, tangled up just like Gödel's original statement G.
Oh.
But they look like normal number theory problems.
And it goes even further.
Yeah, even into basic algebra. Things called Diophantine equations, just asking if equations involving sums of integers raised to powers have integer solutions.
Oh.
Seems fundamental, right?
Absolutely.
Matyasevich proved that there's no general algorithm to solve all Diophantine equations. And later work showed that specific instances can actually encode undecidable problems, again linked back to Gödel.
That's the truly astounding and maybe slightly scary thought then. Gödel's work wasn't just about some weird marginal area of logic. It showed that undecidability, unprovability, reaches right into the core of very standard fundamental mathematical questions.
Questions about integers, equations,
Yeah.
things mathematicians study all the time. It means there are concrete mathematical questions out there that simply cannot be answered with yes or no proof using our standard methods.
Okay, so let's just recap the core idea. Gödel showed us that even in these really robust, seemingly complete mathematical systems, there are fundamental truths that just cannot be proven from within the system itself.
Right. And it's not about us not being smart enough yet to find the proof. It's an inherent, inescapable limitation of the system itself.
Which raises this really profound question, doesn't it? If even pure logic and mathematics, which we often think of as the ultimate realm of certainty, have these built-in limits to what can be proven, what does that mean for our bigger quest for knowledge in any complex system of understanding?
Yeah, what are the ultimate boundaries of human comprehension if even the seemingly straightforward world of numbers holds secrets that are fundamentally beyond proof?
Definitely something to mull over. Thank you for joining us on this deep dive into Gödel's incompleteness theorem.